Hey everybody. Today we're talking about continuous random variables. A continuous random variable is one that can take values over an entire range, in contrast to a discrete random variable that can take values only in a non-continuous set, like the number of 6s in 20 rolls of a fair die can only be 0, 1, 2, 3, 4, etc. Can't be anything in between those numbers. Some examples of continuous random variables: the length of the tail of a randomly selected dog at your local animal shelter, the exact temperature at the South Pole at a random moment, or the length of a randomly selected call to a customer service line. Any one of these things could take values in an entire range. Now here it doesn't matter that your measurement accuracy might be just to the nearest centimeter, for instance, or to the nearest second. In theory, any one of these things could be measured as accurately as you like. Probabilities are harder to describe for continuous random variables than for discrete ones because there are uncountably many possible outcomes. For instance, if we're thinking about calls to a customer service line, the call might last 150 seconds, but it could equally last 150.1 or 150.01, or infinitely many other possible values. So in essence, the probability of any particular outcome is essentially zero. And yet, some call lengths seem intuitively more likely than others. It's more likely that you have a 30-second call than a 30-minute call, for instance. And we need to be able to talk about the probabilities of continuous random variables in a more meaningful way than just to say that they're always zero. And the way we do this is by considering ranges of possible values. And we write things like the probability that x is between 140 and 160. Here I'm thinking about x as being the length of that randomly selected call from that call center measured in seconds. One way to visualize a continuous random variable is with a density curve. And then probabilities over ranges are understood to be areas under the curve. So here I'm showing the graph of a random variable x that can take values from 0 to 4 with decreasing probability. So we're seeing that probability density curve going down. We find probabilities by computing areas under the density curve. So here I'm illustrating the probability that x is between 1 and 2 with that shaded area. Notice that this probability will be less than the probability that x is between 0 and 1, even though those two intervals have exactly the same width. There'll be less area between 1 and 2 than between 0 and 1. And there'll be even less area between 2 and 3 than between 1 and 2 than between 0 and 1. We can use the density curve to actually estimate probabilities. So just looking at this picture, I'm estimating that shaded area is about 0.30. And so that estimates the probability that x is between 1 and 2. Now, if you know the equation of the density curve in a little calculus, you can do an integral and find the actual area. But in college statistics, we're not working at that level of complexity. The function defining that graph is called the probability density function, or PDF, as I mentioned a moment ago. And it has to have two basic properties. First of all, it always has to be positive for all values of the random variable, just because probabilities are always positive. And the total area under the graph has to be 1. And that makes sense because the total probability in any probability experiment has to be 1. So if we're talking about a continuous random variable, the area under the whole graph is the total probability in that probability experiment. Usually when we have a continuous random variable, we can compute probabilities using the cumulative distribution function, or CDF, which represents the probability that the random variable takes on a value no greater than the specified value little x in a given trial. So using that same density curve that we had a little bit ago, we can illustrate the cumulative distribution function like this. Here I'm drawing big F of 2. The cumulative distribution function at x equals 2, the probability that x is less than or equal to 2. Notice that as x gets bigger, big F of x always gets bigger too. The probability accumulates. The reason we are so focused on the CDF when computing probabilities of continuous random variables is that we can use it to compute the probability that the random variable falls into any given range that we're interested in. So to find the probability that x is between a and b, we take big F of b and we subtract off big F of a. So the cumulative probability at b minus the cumulative probability at A. Geometrically, what we're doing is we're taking the shaded area we're finding the shaded area in the graph, like I'm showing here, by taking the area to the left of the rightmost endpoint and subtracting off the area to the left of the leftmost endpoint. In this case, the area to the left of 2 minus the area to the left of 1. For any individual value x in a continuous probability distribution, the probability that x is equal to x is 0, as we mentioned earlier. And that's helpful because it means we don't have to worry about whether our inequalities are strict or not. So we can be a little bit sloppy when we're computing the probability that x is between a and b. It doesn't matter if we write less than or equal to in each of those inequalities. Now, that is not the case with discrete random variables, so fair warning there. This only applies to the continuous case. The simplest continuous random variables possible are those with uniform distributions. And a uniformly distributed random variable is just one that takes on equal probabilities on intervals of equal widths. In other words, it's a random variable with a constant PDF, basically constant probabilities everywhere. So here's a visualization of the uniform distribution on the interval 1, 7. Probabilities are equal throughout that interval and 0 otherwise. The PDF has to be equal to y equals 1/6 because the total area has to be 1. We have a rectangle of width 6, so the height has to be 1/6. For instance, here's a picture of the probability that x is between 2 and 5. That probability is going to correspond to the shaded area. And in this case, half of the area under that graph is being shaded between 2 and 5. So the probability that x is between 2 and 5 is 1/2. To say it a little bit differently, the interval 2, 5 is half of the interval 1, 7. So we can do the probability just by computing the ratio of the interval that's included, because all the probabilities are equal. A bit more mathematically, the probability that x is between 2 and 5 is 1/6, the value of the PDF, times 5 minus 2, the width of the interval that we're looking at. Either way, we get 1/2.